So in part one of this series, I described how the sun is going to sleep and that we're actually in an ice age and that there's no more solar flares, and solar flares is actually a predominant factor of the solar wind, our magnetic field, and our weather. Our weather can be coupled and linked to the sun, and that we're headed into another ice age, and I discussed solutions to energy, the energy that we're going to need. And you see, this is a 22-year cycle of sunspots, and it's basically, that's the full cycle. The last one was cycle 24, and we're going into the minimum, the grand minimum, which is really incredible. The floor is just falling out. So the sun is really going to sleep, and that's going to have a profound effect on our weather. Ben Franklin said it was the summer that wasn't. So we have to get our act together, and the big thing we have to get together is on energy. Energy is going to be life, and as I'm going to show you in this video, the Mandor minimum, which was last time, I think we're headed into another one, if not even a bigger minimum, and as well as the magnetic field is flipping, so cosmic rays are at a maximum, and this is the picture of the sun right now. So in part two, we're going to discuss these solutions and what we can be done about it. These are the cycles of the sun for approximately the past 30 years, 35 years. Now, interesting enough, this is the number of sunspots, okay? And remember, with sunspots, we have solar flares. And as I was showing you, those flares partake a certain amount of energy that's radiated in the solar wind to the Earth and to the rest of the planets in the solar system. So you'll see cycle 22 is up here. It was a minimum. And cycle 23, now the minimum here bottomed out. And cycle 24. And you can see that we're already bottoming out because there have really not been any solar sunspots. And as you can see, this line here, look at the slope of this. You see the slope of this line right here? You see the slope? So it doesn't take a rocket scientist to figure out that we're headed into another mini ice age, if not entering it already. Like I said before, the thermosphere is cooling at an alarming rate. Now, this has happened before. So there is a chart here where there's 400 years of sunspot observations. It goes back to 1600, and it projects up to 2050. Now, as you can see, in the 17th century, there was a mini ice age, and that was called the Mandor minimum. Okay, and you could see that it flat spotted right here. Okay, and it was a mini ice age, and there was another dip called the Dalton minimum right here. All right, now as you can see, there's cycles like the Glassberg minimum right through the beginning of the 1800s. Okay, and here's the modern maximum, right? 1950s, right? See how high we are to the average? Okay, and now we're headed down, and we've been headed down. So the Earth's been getting cooler steadily, okay, to the what they call the Eddy minimum, which is another mini ice age. But this could be an actual grand solar minimum, and that depends on other factors also. It has to go with our orbit. I'm going to show you that as well. There is a so-called habitable zone, okay? Which means if you're Venus, it's too hot. If you're Mars, it's too cold. If the Earth, it's just right. Now, this is the actual orbit of the Earth around the Sun. And as you can see, it's an elliptical orbit that moves with the planet Jupiter. See that? See how it's dragging the Earth around? The Sun also wobbles a bit too, but you can't see that. So now, if you look at the noon sky at noon every single day, you'll see that it marks a shape. And this shape is basically an aphelia. Now, this symbolizes the two positions from the tilt of the Earth's axis, from the solstices, which are two extremes, the top and the bottom. Okay, and as it tilts to the Earth, you're going to get different seasons. And the Sun is going to move up and down in the sky because of the tilt of the Earth. Now, actually, in the northern hemisphere, in the winter months, we're actually closer to the Sun than in the summer months, we're actually farther away. Now, that makes, when it's equal, it's called basically the equinoxes, and then we have the solstices in the top and bottom. And this is what the Sun looks like if you viewed it from the Earth. I mean, the Earth looks like if you viewed it from the Sun. Basically, 365 days a year as it goes around the Sun. And then this is what it would look like in 100 years as it travels through space, because the Sun is actually traveling through space around in 100 years of time. Now, because I'm explaining this to you, everything has a thing on it. So it's not just that. So there is a solution. I'm showing you the Epcot Center. This is the land exhibit. And you're going to see that with electricity, you can actually make a difference. You can make food. You can make your environment. You can, because we're going to lose approximately 1,400 to 15,000 square miles of farmland. But in these geodesic domes, we can make food in hydroponic gardens. And they've done this. They have a full exhibit. It's sponsored actually by NASA. And basically, there's the plants actually produce waste that actually feeds fish. And the fish waste feeds the plants. And it's unbelievable. But the key element is that the whole system runs on electricity. So it's very important that we have to institute clean electrical power and modular power, which means approximately 200 megawatt units installed in towns and little cities. And in a metropolitan area like Manhattan, you'd have, say, 20 of these units running. That would make our electrical system extremely modular, and it would allow us to be able to survive the famine that's going to happen as this mini ice age grows. So it's very important that the lessons are learned, and these possibilities are things that can happen. Tremendous amounts of food, and look, there's technologies out there that can print steaks, for example. They're, like I said, these things, they actually feed. We ate at this place. Salad and fish and the food were all grown at this land exhibit at the Epcot Center down in Disney World, Florida. Basically use 91,000 kilowatt hours in the Western world of energy per person per year. That's all energy. So that would include transportation, heating, cooling, wash and dryer, water, everything that makes your modern civilization technology life go. Okay? And with thorium, as I've reviewed before, you can get that down to this much of thorium. Okay? Now you're saying, what is thorium? All right. So we all know what uranium is. It's element 92. It's on a periodic table. This is a periodic table. And thorium is right over here. It's 90. Now, natural thorium is very, very abundant. Okay? Which means it's basically everywhere. And unlike uranium in reactors and other plutonium and whatnot, it's not a fissile material, okay? It's a fertile material, which means that you have to change it to another element by bombarding it with a neutron to make it into essentially a fissile thing. So, I know we have that chart. So this Alan Weinberg, he's basically the creator of a lot of our, well, he patented the first nuclear reactor, which was basically set up for the Navy at Shippingport. But that was a 60 megawatt unit. So the Navy really didn't care about the so-called costs or efficiencies and whatnot. They basically just wanted a power plant that didn't need a chemical reaction to run, so they could, run nuclear submarines anywhere. Okay. So when they dial this thing up to scale to be like 1,000 megawatts, the problem is the pressures. The pressures are horrific, and that's where you would have a failure because it was never designed that way. So he came up with the molten salt reactor, and they actually had an actual molten salt reactor running at Oak Ridge from 1959 to 74. And there's new designs put out by Vid Ref, which is basically a lifter, and you can look this up. I think I'll attach a video. I might put a video to this type of technology that was done by a group of the thorium people and Vid Energy. It's very, very well done video. And basically, this uses what's known as called fluoride, not fluorine, fluoride salts. So instead of you having basically a liquid moderator such as water inside of solid fuels, you have a solid moderator such as graphite inside liquid fuels. And there are two liquids that are in the system. You have a thorium fluoride solution and uranium 232-233 solution, which is in the actual core of the moderator, which is producing the reaction, the nuclear reaction, and getting hot. As the thorium is hit by the neutrons, it's turned into protactinium. Getting really deep in the woods. Point is, this is an extremely safe design. It doesn't depend on any outside source or outside water or anything like that. If there is a loss of power or anything like that, This freeze plug melts. Everything goes into the drain tank. Without the moderator, there is no nuclear fission taking place, so it just cools off and becomes a rock hard salt. Even if this did spring a leak, it would instantly turn into salt crystals like your table salt that's on your table. And thorium is very abundant. Like I said, you could basically dig dirt and rock anywhere in the country and you're going to come out with it. But we really don't have to. There is thorium in the United States. There's tons of it. We're one of the top 3 countries in the world that have reserves, and again, the world energy reserves, that if you ran it on thorium, would be approximately 5,000 tons a year, which is what you would really pull out of any rare earth mine through monazite. So as you can see, we have 400,000 tons in this country alone. Now the other beauty of these reactors is that they will digest anything, which means they can run also on spent fuel from old pressure water reactors and pressure and boil water reactors, which is approximately 8 million tons of that stuff all over the earth. So you can again burn that fuel up, turn it into a harmless salt, making electricity cheap all the way. So this is really fantastic technology that really has to get the light on. And again, these are pictures of that reactor running at Oak Ridge, and what they did is they just put it into a heat radiator and stuff, and they got it up to 1,000 megawatts, which is incredible, right? So this is Kirk Sorensen from Flive Energy. He is really responsible for discovering this tech and bringing it back. He used to work for NASA, and he has his own company, Flive Energy, and this is the design he came up with, the 2-fluid reactor core, and this is the cycle of the thorium. So for example, here's your regular common thorium, okay? So when it's hit with a neutron, it turns into thorium-233, but quickly decays to protactinium-233, which is easily separated in the liquid, and it's put into a decay tank for 30 days, which then turns into uranium-233 and uranium-232. Those two elements are actually fissionable. And in the thermal spectrum, they actually will put out 2.5 or 2.3 neutrons. Now, the advantage of this system is that it works not on pressure, it works actually at low pressure. It doesn't work on, actually it's lower than atmospheric pressure. You could consider it a partial, close to a vacuum. And the other thing about salts is that they have 1,000 centigrade of heat temperature range. So you're working on temperatures that are much, much higher than your standard water reactor. You're talking about temperatures where you can do fantastic processes, such as one of the most energy complex tasks to do is make fertilizer. And this type of reaction, you'll be able to do all those complex things, as well as you can use that heat and electricity to run a very high efficiency CO2 turbine. And you can also recycle everything from steel to all these things that we don't recycle today. You'll be able to recycle them because you'll have the temperatures to do it. Now, any type of reactor like this is 1,000,000 times more efficient than a chemical reaction, than an actual carbon-hydrogen bond. And that's the main reason why you want this. You can also use this system to make synthetic fuels very inexpensively. So by doing this, you don't throw away the full point so-and-so trillion dollars worth of hardware that's out there, such as diesel engines and cars and whatever, because you'll be able to maintain that structure for at least 15 years, 16 years, but then you'll be able to use this to produce new items. And that's very important. So these are tables as far as the fission products and atomic numbers. And as we've said, the closer you are to this part of it, the less nasties you're going to have in the decay chain. And with this type of reactor, you can get efficiency up to 98% of consuming all the radioactive material that's in there and ending up with really very, very good salts. So this is the end of my We're in an Ice Age Part 2 series. And I just wanted to thank you guys again for all my subscriptions, your well wishes. I want you guys to have an extremely Merry Christmas. Please be safe. And thank God for the birth of Jesus Christ, our Savior, which is really what Christmas is about. And give all your family members a great big hug and be thankful. And because I'm thankful for you guys. And I want you, if I don't make a video again because I'm going away, have a great and happy new year. Okay? God bless everybody.